Right, so intermolecular forces and intermolecular forces refers to the forces due to interactions of molecules, and the reason we're interested in those is that they're useful for explaining properties of substances. Okay, so the properties of substances pretty much depend on the strength of the attractive forces among the particles that make up your substance, okay, like the molecules. And generally, if you have stronger attractive forces, it leads to higher melting point, higher boiling point, higher viscosity, and higher surface tension. Let's try to understand why it requires higher boiling point or higher melting point when you have stronger forces of attraction among your molecules. What happens when your molecules are strongly attracted to each other? It's harder to spread them out, right? It's harder to pull them apart. So what happens in boiling when a liquid boils? You're spreading out your molecules. So it takes more energy for them to overcome those forces of attraction. So you would expect a higher temperature. A higher temperature simply means you have more energy for your molecules. Same thing with melting point. Going from solid to a liquid, in the solid, the motions are more restricted. There's more freedom of movement in the liquid as opposed to a solid. So for them to have that, the ability to move better, okay, they need to have a higher energy. Okay, if you have a stronger forces of attraction among the molecules, you need a higher energy to overcome those forces of attraction. Viscosity is the resistance to flow. Okay, and so that's also higher viscosity is also associated with attractive forces. Surface tension. Surface tension has to do with increasing the surface area of your sample. Okay, so that requires movement of molecules from the bulk to the surface. And anytime you move molecules from the bulk to the surface, that also requires energy. So surface tension is in fact defined as the energy required to increase the surface area. So that again, that involves overcoming forces of attraction among the molecules. Okay, so stronger attractive forces would lead to higher melting point, higher boiling point, higher viscosity, and higher surface tension. Here's an example. What does the fact that oxygen, O2, is a gas, while H2O is a liquid at room temperature imply about the strength of the intermolecular forces? O2 is in the air that you breathe. It's about 20% of the air you breathe. It's a gas at room temperature. Whereas water, water is what? Water molecules are much closer together at room temperature. It's a liquid, right? So what does that mean? In which case do you have stronger attractive forces among the water molecules? Okay. In fact, that means that your oxygen, what would you say is the boiling point of oxygen? It's going to be way below room temperature, right? If it's already a gas at room temperature, that it must, if you imagine it was a liquid at some low temperature, it would boil at a very low temperature before you even reach room temperature. It's already a gas at room temperature. Okay, so intermolecular forces can be classified as either van der Waals forces, which are considered relatively weak forces, and hydrogen bonding interaction. Among the van der Waals forces, you can classify those as dipole-dipole interaction, London dispersion forces, which is the predominant type, okay, and it's present in all molecules. Between any pair of molecules, you will have London dispersion forces, and then you can have what's also known as dipole and induced dipole interaction. We're going to go through those. Hydrogen bonding is significantly stronger than van der Waals forces for small molecules, and these are special cases where there are specific cases where this could occur. Okay, and so we're going to look at that in this lesson. So let's start with dipole-dipole interaction because that's an easier one to understand, the easiest one to understand. In a dipole-dipole interaction, you have attraction between polar molecules. Okay, so if you have a HCl, for example, is what we call a polar molecule. There's actually a higher concentration of electrons on the chlorine end of the molecule. So we say that chlorine end of your molecule has a partial negative charge. So that delta with a minus sign next to it means partial negative. And there's a partial positive charge on the hydrogen. So, and the reason for that is there's an unequal sharing of electrons between hydrogen and chlorine. So we say the bond between hydrogen and chlorine is polarized in the direction of chlorine. So, if you have a hydrogen chloride molecule near another hydrogen chloride molecule, what's going to happen? The positive end of the other molecule is going to be attracted to the negative end of the other the neighboring molecule. So what the interaction you have between those two is called dipole-dipole interaction. Remember, opposites attract, right? So that's dipole-dipole interaction. So that's the type of attractive force that occurs between polar molecules. The positive end of one polar molecule will be attracted to the negative end of another polar molecule. So exactly what do we mean by when we say we have a polar bond? We said that's when the shared electrons spend more time near one of the two atoms. Okay? You can define what's called the bond-dipole moment. It's a vector quantity, so it's got magnitude and direction as a measure of bond polarity. Okay, so bond-dipole moment is given by the partial charge, okay, times 1.602 times 10 to the negative 19 coulomb. This is the charge of one electron, also the charge of one proton. It's negative for an electron, it's positive for the proton, times the distance r. Okay? So, in other words, if you imagine a proton and an electron separated by a distance r, okay, what would be your dipole moment for that? Then you'd have a full charge, okay, a full unit of charge. One electron is negative 1, one proton is positive 1. So delta is equal to 1 there, okay? It's full charge actually, so it's not a partial charge. Times the charge of the electron or proton, which is 1.6 times 10 to the negative 19 times r. That would be the dipole moment. But in a bond, okay, you say there's a partial charge between the two atoms. So you multiply the full charge. Your delta right here would be a number between 0 and 1. Okay, so that gives you what we call the ionic character of the bond, the extent to which electron has been transferred from one end of the molecule to the other. Okay, so r here is the bond length. So what's the unit for dipole moment? The unit is a debye. The official abbreviation for the debye is capital D. And it's 3.336 times 10 to the negative 30 coulomb meter. Okay, where does that unit come from? A unit of charge is a coulomb. SI unit for length is meter. So your unit for dipole moment is a coulomb meter. So here's an example. HF, the molecule HF, is experimentally found to have a bond length of 92 picometers. So if you have hydrogen and fluorine, okay, and you look at the separation of the two nuclei, the average separation is 92 picometers. So that's 92 times 10 to the negative 12 meters. And the experimental dipole moment can be measured to be 1.9 debye. So what's the partial charge of HF? How do you solve for the partial charge or the ionic character? What was our formula? Mu equals partial charge times 1.6 times 10 to the negative 1.602 times 10 to the negative 19 coulombs times r. How do I solve for delta? Divide both sides by this, right? So 1.602 times 10 to the negative 19 times r. So delta equals dipole moment 1.9 debye oops, sorry, 1.9 debye over 1.602 times 10 to the negative 19 coulombs times distance in this particular case is 92 picometers. So 92 times 10 to the negative 12 meters. What is the debye? You have to change that unit. to Si. What's 1 divided? 3.336 times 10 to the negative 30. Coulomb meter. Okay, so divide cancels out. Coulomb and meter cancel out. So you just get your partial charge or ionic character. And that's equal to how much? You have a number for me? You should come up with about 0.43. Let's see. Okay, so 1.9 times 3.336 times 10 to the negative 30 divided by 1.602 times 10 to the negative 19 divided by 92 times 10 to the negative 12, 0.43. Okay? So we say that our ionic character is 0.43, or we say it's 43% ionic. Okay? So you might say that a transfer of one electron, a net transfer of one electron from one atom to another, we say is 100% ionic. But because the electron transfer is not complete, we say we have a polar bond, a polar covalent bond, which is only 43%. The electron is only 43% transferred from one to the other. So that's how you get a polar bond. So dipole interaction occurs when you have polar molecules, between polar molecules, and you can get a polar molecule if it has a polar bond. Okay? But it doesn't mean that if a molecule has a polar bond that it is polar, because if you have a molecule that has more than 2 bonds, it's more than 3 atoms, then those polar bonds could end up canceling each other out. So you may end up with a molecule that's not polar, even though it has polar bond. So when we say a molecule is polar, okay, it must have we say it has a non-zero dipole moment. The dipole moment for a molecule will just be the sum of all the dipole moments for the bonds. Okay, so you get a polar molecule if your bond dipole moments add up to a non-zero value. They don't cancel each other out. So how can you tell if you have a polar molecule qualitatively? First of all, it has to have at least one polar bond, right? But if there's more than one polar bond, they must not be symmetrically oriented. For example, carbon dioxide is nonpolar. If you look at carbon dioxide, here's a model for carbon dioxide. Oxygen is more polar than carbon, okay? I mean, it's more electronegative than carbon. So the CO bond, we say, is polar. So there's the carbon to oxygen is polar that way. This carbon to oxygen bond is polar this way. These polarities cancel each other out. So the vector sum of those two dipole moment vectors is 0. So even though carbon dioxide has 2 polar bonds, the molecule itself is nonpolar because of the symmetry. What about water? Here's your oxygen and here's your hydrogen right here. You have a polarity towards oxygen. Okay, oxygen is more electronegative than hydrogen. So there's a polarity going that way and there's another polarity going this way. Okay, so you can see there's a net polarity towards the oxygen end of the molecule. So we say that a water molecule is polar. Okay, so that's how you can tell if you have a polar molecule or not. So how do you actually measure molecular polarity? What you do is you put your sample between electrically charged plates. A pair of electrically charged plates is what's called a capacitor. Okay? So you put your sample in there. So if one's end is positive, the other one's negative. Okay? Capacitor is something that can store a charge. So if you were to hook up like a capacitor to a battery, for example. Okay. All right, so let me put a switch over here. So if I were to close this switch, what's going to happen? This is the negative end of the battery. That's the positive end of the battery. Okay. So if I were to close this switch, okay, electrons will have a tendency to flow from the negative end of the battery to the positive end. So electrons will flow this way. Okay, but then because of the gap here, right here between the two plates, okay, it, the current flow is just temporary. It will just flow for a little bit and then it will stop. So there's a limit to how much electrons can be stored over here. Okay, by putting a polar molecule in between these two plates, you can polar molecules between those two plates, you can actually increase the ability of your plates to store extra charge, to store electrons. Okay, so that's how you can measure polarity. We're not going to go into detail as to how that measurement is done. Just to give you an idea as to where that, I just want to give you an idea as to where that experimental measurement, how that experimental measurement can be made for dipole moment. Okay. If you want a better simulation of that, let's see a better picture of what's going on there. Let's go to phet.colorado.edu. There's a simulation there on molecular polarity right here. So if you run that simulation, you'll see okay. So if I turn on my electric field, I'm basically putting a charge. So this is now positive, this is now negative. Okay, so I'm hooking that up to a battery. And this is the positive end of the battery right here. Okay. And if I put a polar molecule in between those two charged plates, what happens is this. First of all, let's say right now, the way this is set up is my electronegativity for A is lower than that for B. So what do you notice? B is more electronegative, so electrons that are shared between A and B are polarized towards B. So we have that arrow pointing towards B. That's what the bond dipole arrow tells you. Okay? If I put the partial charges on, you can see that the partial negative symbol is written next to B. It's partial negative, partial positive. We say B is more electronegative than A. And the bond character we say is polar. Okay? So it's between pure covalent and pure. So on this side it's more covalent, on this side it's more ionic. It's somewhere in between. Okay, so polar covalent bond. I can actually show the electron density right here. And you'll notice it's a little darker. It's grayer on this side. Okay? On the B side than it is on the A side. All that is telling you is that there's a higher electron density around the B atom. We say B is more electronegative. What happens if I make A more electronegative than B? I drag this one over here. What do you notice? Ooh, what happened? I make A more electronegative, then what happens to A? It becomes partially negative charged, right? So the A now is partially negative. It's now attracted to the positive plate, positively charged electrical plate. Okay, and you can see this one's dark. The shading right here is darker. That means you have a higher electron density near atom A. Okay, now what happens if I were to turn this molecule? Oh, what happened? Right there. So your the A atom, the partially negative end of your molecule is attracted to the positively charged plane. Okay? All right, so that's how your polar molecules will behave if you place them between electrically charged plates. So based on that behavior, you can make measurements that would allow you to determine the dipole moment of your molecule, to determine whether it's polar or not. So how do we predict bond polarity? If you recall, ionization energy increases left to right, okay, across a row in your periodic table, and so does electron affinity. And so what is ionization energy? A measure of how hard it is to remove an electron from an atom. And electron affinity is a measure of the ability of an atom to accept an electron, right? So the higher the electron affinity and the higher the ionization energy, the higher the electronegativity. Now, Linus Pauling invented a scale for electronegativity, which ranges from point set, where he assigned values. Okay, on his scale, francium, which is on the bottom right corner of your periodic table right here, is assigned an electronegativity of 0.7, and fluorine, which is right here in the upper right-hand corner of your periodic table, has the highest electronegativity. So given a value of 4.0. Okay, he based those values on bond dissociation energies, and he compared the bond dissociation energies with the experimental dipole moment of HCl, HBr, and HF, and he came up with a formula that relates the partial ionic character, the ionic character of a bond, to the difference between electronegativities. Okay, so delta En right here is the difference in the electronegativity between two atoms that are in a bond, and you can calculate the partial charge, your ionic character. Okay, as 1 minus e to the minus delta En squared over 4. Okay, you can classify bonds as polar or nonpolar depending on the difference in their electronegativities. If the electronegativities are the same, so the difference in electronegativity is 0, then you have what's called a pure covalent or nonpolar bond. Okay, your ionic character is 0. Why is that? Delta would be 1 minus e to the 0 over 4, right? 0 squared. So 1 minus, what is 0 squared divided by 4? 0. What is e to the 0? E to the, anything raised to the power 0 is 1. So what's 1 minus 1? 0. Okay, so if you have two atoms with the same electronegativity, then we say the bond between those two atoms is pure covalent. Now, if the electronegativity difference is larger than 0, okay, then you have what's called a polar covalent bond. But typically, okay, we have what we might say are rules of thumb that say if the electronegativity difference is greater than 2, we say that the bond is essentially ionic. Okay, what does that mean? Let's calculate delta if the difference in electronegativity is 2. Delta equals 1 minus e to the negative 2 squared over 4. Right? If the difference is 2, so that's 1 minus e to the, what's 2 squared over 4? 1, right? So what's 1 minus e to the negative 1? That's 1 minus 1 over e, okay? Or 1 minus e to the negative 1. So how do I get e to the negative 1 on my calculator? I'm going to say negative 1 inverse natural log. E to the x is just the inverse of e. Raising e to the power x means taking the inverse of the natural log. Okay? So I'm going to say I have negative 1 inverse, here's e to the x, right here. Okay, so it's 0.37. So it's 1 minus 0.37, so that's about 0.63. So you say 0.63 would be 63% ionic. Okay? So what we call a 63% charge transfer from one atom to another, we say that bond is essentially ionic. That electronegativity difference is big enough, so we can say that the bond is essentially ionic. So the larger the difference in electronegativity, the greater the ionic character. Here's a way of looking at it. If I make A way more electronegative than B, okay, so you increase your partial charge, your molecule becomes more and more polar. Okay, so you have so you say your bond is more ionic. Now, when the electronegativity is less than 0.5, okay, when your electronegativity is less than 0.5, you'll find that your partial charge would be less than 6%. The transfer of electrons between the two atoms is less than 6%. We say that even though, strictly speaking, the bond is polar covalent, it is still polar covalent. We say that because that difference is so small, we say that the bond is essentially nonpolar. Now, keep in mind, these are just rules of thumb, and they vary depending on textbooks. Some textbooks would have 1.8 as a threshold between ionic and covalent. So this is just, you might say, rough rules that you can use to gauge whether you're looking at an ionic bond or a nonpolar bond or a polar bond. Okay, so keep those in mind. So that's what you need. Okay. So let's look at a couple of examples here. Let's classify the bond between carbon and hydrogen. Carbon and hydrogen. So you can look up tables for electronegativities. You'll find hydrogen's 2.2. Pauling originally assigned that a value of 2.2. Okay, and carbon's 2.5. Although in a later paper, Pauling changed that to 2.1. So you might see 2.1 in your textbook. What's the difference between carbon and hydrogen? A difference of 0.3. So a carbon to hydrogen bond, we say, strictly speaking, it's polar covalent. But for practical purposes, that difference is so small, we say the bond is essentially nonpolar. So CH bonds are generally considered as nonpolar bonds. What about lithium and bromine? Lithium's 1.0, bromine is 2.8. So what's 2.8 minus 1.0? 1.8. That's a very large difference. So we say it's a polar covalent bond. It's almost pretty much, it's essentially ionic. Okay, you're up there close to 2. So that's an essentially ionic bond. Now, I did give you a 2.0 threshold cutoff, right? And that's a gray area right there. So it's, the best thing to say is that it's very polar, okay? Because there's really no such thing as 100% ionic. How can you get a 100% ionic anyway using Pollys formula? How might you make that for 100%? What would have to be the electronegativity difference in order for delta to be equal to 1? What's the largest possible electronegativity difference you can get between francium and fluorine, right? Based on his scale, what's 4 minus 0.7? 3.3. But what is 1 minus e to the 3.3 squared over negative 3.3 squared over 4? Let's put that in your calculator. Okay, so 3.3 squared, so 3.3 times 3.3 divided by 4. Okay, make that negative. Okay. Oops, is that what I have? Okay. Oops, I'm sorry. Negative. Let's do it again. 3.3 times 3.3 divided by 4. That's 2.27225. Make that negative. And then take the inverse log of that. It's 0.06. Okay, so that's 0.066. Subtract that from 1. So minus 1. That's 0.934. So that's only 93.4% ionic. Okay, so there's using this formula, you can't even get 100% ionic. So it's really just there's really no theoretical basis for this formula. He just used it to fit his experimental data. So you can just use that as a gauge, a rough gauge as to whether or not you're dealing with something that's ionic or polar covalent or covalent, nonpolar or polar. Right? What about sodium and chloride? Would that be an ionic bond or polar or a nonpolar bond? Sodium is 0.9 and chlorine is 3.0. What's that difference? 2.1, that's essentially ionic. Okay, sodium chloride is an ionic compound. All right, so how do we reconcile this with your earlier lesson where you were told metal plus nonmetals ionic, two nonmetals covalent? Well, two nonmetals will generally give you covalent, polar covalent at the most, all right? But if you have metal plus nonmetal, okay, that's why I'm very careful when I teach this to my class. I say metal plus metal tends to be ionic. But you can see there's going to be a lot of exceptions you'll see here. In fact, a whole class of metals, the transition metals, the electronegativities are such that the difference between those and a nonmetal are, if you go by this classification of bonds, they're not really going to be classified as ionic. So there's really, ionic is really just an extreme case of 100%, what you might consider 100% polar covalent, but it's really, most bonds are really somewhere in between, okay? Which pair of atoms would form a bond where the polarity is directed towards the first atom? So in other words, if I have atom A and atom B, so this is atom A and atom B, in which case will the polarity be directed towards A, the first atom? Is it between C and C, H and F, O and C, or I and Cl? Here's your electronegativities. Hydrogen is 2.2, carbon's 2.5, oxygen's 3.5, fluorine is 4.0, iodine is down here. You know, what's the trend there? Chlorine is 3.0. So what would be the answer here? In other words, what's another way of asking this question? If polarity is directed towards the first atom, what does that mean? Which atom is more electronegative? Polarity is directed towards the more electronegative atom. So another way of asking this question would be, for which pair is the first atom more electronegative than the other? Ready? One more? Correct answer is okay. Which one's more? Obviously, it can't be A, right? Did anyone pick A? No, good. It can't be A. Which one's the most electronegative atom? Fluorine, right? So HF, where's the polarity directed towards? Fluorine, so it can't be B. O and C, which one's more electronegative? Oxygen, so polarity is towards oxygen, so it can't be C. I and Cl, what's the trend in electronegativity? Away from fluorine, it's decreasing electronegativity, right? So look, 4.0 to 3.0, 2.8, iodine, you expect that to have a lower electronegativity. Think of electronegativity as increasing towards fluorine. Fluorine is the most electronegative atom. So I and Cl, which one's more electronegative? Chlorine, so the polarity is towards chlorine. So what's the answer? Oops, sorry, it's O and C. C. It's towards O. Okay. All right. I wrote it this way, so it's towards O. So the correct answer is C. All right, so correct answer is C. Very good. All right. Which pair of atoms would form a polar covalent bond but essentially nonpolar bond? Ready? Okay, nitrogen. Let me go ahead and start the poll while I try to explain. Nitrogen has 3.0. Hydrogen's 2.2. Carbon's 2.5. Chlorine, sodium is 0.9. Chlorine is 3.0. Beryllium is 1.6. Iodine is 2 point something, less than 2.8. How would it be? Carbon and hydrogen. Difference is very small, right? Difference of only 0.3. That's, although it's technically a polar covalent bond, for practical purposes, we say that bond is essentially nonpolar. Yes?
So the slide you had before this, the reason why it was zinc was because of which element you had first?
Yeah, because I wrote oxygen first.
If B would have been switched, it would have been B.
Yes. Mm-hmm. The way the question was phrased, it says polarity towards the first atom listed, in which case I wrote oxygen first on that one. Okay, how about this one? Which of the following is or are true? Number one, a non-polar molecule can have polar bonds. Number two, a molecule with no polar bonds is nonpolar. Is it one only, two only, both, or neither? What does a molecule need to have to be polar? At least one polar bond. But if it has more than one polar bond, those polar bonds must not cancel each other out, right? Because due to the symmetry of the molecule. So how would you evaluate these questions as far as being true or false? Is it one is true only one is true, only two is true, or are they both true, or are neither one true? Okay, let's see. A non-polar molecule can have polar bonds. Is that true? Yes. What's the example we have? Carbon dioxide, right? It had polar bonds, but it is nonpolar, so that's true. Okay, so it can't be D. A molecule with no polar bonds is nonpolar. It has to have at least one polar bond, right? So this is also true. So C is correct. Good. Okay, which of the following is polar? H2O, BF3, CH4, PF5. This is the case where it's a question where you have to remember your molecular structure and geometry. Okay, so that's why I wanted you to review that. Here's water. You have a tetrahedral geometry around the oxygen atom, and the molecule is bent. BF3 is trigonal planar. CH4 is tetrahedral. And PF5 is trigonal bipyramidal. So which one is polar? A, B, or C? Or D? It's actually an easy one, because you didn't even have to know the others, right? You already know one of these is polar, which is what? Water. Very good. Now, why are these other ones non-polar? Trigonal planar, you have three polar bonds symmetrically directed 120 degrees apart, right? So there's a symmetry here. So all of these polarities cancel each other out. Okay, imagine you have a tug of war where you have three equally strong people pulling on the center. Now, it's a three-way tug of war. Okay, the same thing right here, tetrahedral structure. That's a perfectly symmetrical structure. Okay, so all of those polarities can actually, these are very, very nonpolar. These are very slightly polar bonds, essentially nonpolar, right? CH bond, you said earlier, was not even Okay, I even have the wrong polarity here. It should be what? No, let's redo that. CH4. A CH bond. Which way is the polarity directed in a CH bond? Carbon's more electronegative than hydrogen, so it's polarity towards carbon, right? But those are very weakly polar bonds, so, and they're all symmetrically arranged, so you expect CH4 to be a nonpolar molecule. PF5, same thing. You have polar bonds, okay, directed towards the fluorine, but all of those polarities cancel each other out. Not necessarily. For example, ammonia. Okay, if you have ammonia, yeah, it's a trigonal planar, trigonal pyramidal geometry. We have that lone pair right there. You have a tetrahedral center, right? So you have three polar bonds. Oh, I'm sorry, I got the wrong arrows. Nitrogen, hydrogen. So you have three polar bonds that way. Okay, so there's a net polarity towards the nitrogen. So you have three polar bonds. They don't, because the molecule's not perfectly symmetrical, those polarities don't cancel out. Your molecule itself is polar. NH3 is a polar molecule. Okay, so anytime you have perfect trigonal planar, or so you have a trigonal planar where all the bonds are equivalent. If you have trigonal bipyramidal where all the bonds are equivalent, or if you have tetrahedral where all the bonds are equivalent, or you have linear molecule where all the bonds are equivalent, then you know it's polar. Okay? I mean non-polar because of the symmetry. All right, let's look at this one. For which pair of molecules does dipole-dipole interaction occur? Between H2O and CO2, between H2O and HF, between CO2 and CO2, or between CH4 and CO2? What would you have to do to know to be able to answer this question? When does dipole-dipole interaction occur? When you have two molecules that are both polar, right? So another way of asking this question would be, in which case do you have, are both molecules given polar? So what do we know about water? Water is polar, right? So water is polar, but carbon dioxide is not, right? So you can't have dipole-dipole interaction there. So carbon dioxide is nonpolar. You can't have dipole-dipole interaction there. Carbon dioxide is nonpolar. Methane is nonpolar. You can't have dipole-dipole interaction there. So water and HF, both polar molecules. Okay. So let's talk about London dispersion forces now. The motion of electrons around the nuclei can temporarily lead to polarity. One thing you have to keep in mind is if you have atoms and molecules, electrons are always going to be moving around the nuclei all the time, really fast. In fact, so fast that it's convenient for us to just imagine the electron as just like a blur or a cloud around the nuclei, right? But because they're always moving, at any particular instant, it's possible. It's very likely that you can have what's called temporary or momentary polarization. If you were to take a snapshot of your molecule at any one particular instant, you might find there's a higher concentration of electrons on one end of the molecule versus another. So because of this temporary polarity, so you say that your molecule has what we would call fluctuating dipoles. They're not like polar molecules where you have a permanent dipole. Molecules in general, even though they're nonpolar, they can have what we call fluctuating dipoles or momentary dipoles or instantaneous dipoles. So you can have attractions between these interactions, between these fluctuating dipoles, and so that leads to attractive forces, even though molecules are nonpolar. Okay? Now, larger molecules, the bigger the molecule, okay, the more likely you have the stronger these fluctuating dipoles are going to be. So we say that larger molecules are more polarizable. So you would expect stronger London dispersion forces between larger molecules. Okay? So for which of the following pairs of molecules are the attractions due to London dispersion forces stronger? Between a pair of CH4 molecules or between a pair of C2H6 molecules? Very good. C2H6 molecules are larger than CH4, so they are more polarizable. So you would expect to see stronger London dispersion forces among them. You can just say dispersion forces or London forces or London dispersion forces. They all mean the same thing. Okay. So for which pair of molecules is London dispersion strongest? Between a pair of water molecules, between a water molecule and an H2S molecule, or between two H2S molecules? So you have to go by size, right? So where is what oxygen and sulfur in your periodic table? Group 6A, column 16 of your periodic table. You have oxygen in period 2, sulfur in period 3. What's the trend in size going down a column? Atomic size increases. So which one would be bigger, H2O or H2S? Okay, in terms of size, water will be smaller than H2S. So for which pair of molecules is London dispersion forces strongest? Between a pair of water molecules, between a pair of H2S, or between H2O and H2S? Okay, correct answer is between a pair of H2S. So you would think that H2S molecules would have stronger attractions for each other compared to water molecules, right? So based on this alone, you might say, which one would have a higher boiling point, H2O or H2S? You'd think H2S would have a higher boiling point. They have stronger attractive London dispersion forces. But water is a strange creature. It's a strange molecule. It has a much higher boiling point than H2S. H2S is a gas under ordinary conditions, just like oxygen. And it's a stinky gas. You can actually smell it. And so if you drive by near a paper mill, up in West Monroe over there, you can smell the H2S. So it's a gas under ordinary conditions. Water is a liquid. So water molecules have much stronger attractions. And the reason for that is there's another source of attractive forces, and another reason why water molecules attract each other, and that's called hydrogen bonding interaction. We'll deal with that in just a short while. But based on London dispersion forces alone, you would think the H2S would have stronger attractions for each other than water molecules, but that's not the case. Okay? But if I'm only asking for London dispersion forces, then the answer would be H2S. Okay? But overall attractions, it turns out water molecules have stronger attractions between them than H2S molecules. All right, so let's take a look at this one. Which of the following has the lowest boiling point? O2, F2, or Cl2? Where do you find this in your periodic table? Oxygen, fluorine, and chlorine, right? That's how you find them in your periodic table. Fluorine and chlorine would be in group 7A, oxygen is in group 6A, and oxygen and fluorine would be in the second row. Which one would have the lowest boiling point? What are we trying to look for here? Weakest attractions, right? Weakest attractions would give you the lowest boiling point. So do you have weakest attractions among O2 molecules, or among Cl2 molecules, or F2 molecules? Okay. So if you remember your trends What's the trend going left to right across a periodic table? Increasing or decreasing? Decreasing size, right? So fluorine is smaller than oxygen. What's the trend in size going down a column in your periodic table? Increasing size. So fluorine is smaller than fluorine. So the answer is fluorine. Oh, you need to review your periodic trends in atomic sizes, okay? Which of the following explains why the melting point of iodine is I2, is higher than that of iodine chloride, ICl? A, London dispersion forces are stronger among iodine molecules, which are larger and more polarizable. B, ICl molecules are capable of dipole-dipole interactions, whereas I2 molecules are not. C, both, or D, neither. Think about it. Where would you find iodine and chlorine in your periodic table? Fluorine, fluorine, bromine, iodine. So what's the trend in size? Going down. Size increases. So which one's larger, I2 or ICl? This is larger, right? And what is this thing? The melting point of I2 is higher than that of iodine chloride. Now, which one's polar, which one's non-polar? Iodine is polar or non-polar? Non-polar. ICl is polar. So, what would explain why I2 has a higher melting point than iodine chloride? Is it A, B, C, or D? Ooh. All right. Let's look at the first choice first. Let's look at choice A. I2 molecules are larger. Is that correct? That's correct. They're more polarizable? That's correct, right? So they have stronger London dispersion forces? Yes, that's correct. Does that explain why the melting point is higher? Stronger forces of attraction? Higher melting point. Higher melting point and higher boiling point, right? So that's good. A is okay. How about choice B? ICl molecules capable of dipole-dipole? Yes. I2 molecules not capable of dipole-dipole. Non-polar, non-polar. So they're not capable of dipole-dipole. So that's okay too, right? So the statement is true. Statement B is true, but does it explain why the melting point of iodine is higher? So if ICl is polar and I2 is non-polar, if you're just basing your explanation on polarity, prediction on polarity, what would you predict? The polar molecule you would predict would have stronger forces of attraction, right? And if they have stronger force of attraction, you'd expect them to have a higher melting point. So the polarity cannot explain the melting point. What this is telling you, so this is false. Although this statement is true, it's not consistent with the experimental observation that the melting point of I2 is higher than that of iodine chloride. So this is true, but does not explain the fact. Okay? What that is telling you then is that in this particular case, the primary determinant as to how to explain the melting, as far as the melting point is concerned, as far as attractive forces is concerned, is London dispersion forces. Okay? So, and if you look up your melting points of iodine and iodine chloride, you'll find the melting point of iodine is in fact larger. Okay. Now, what other types of interactions do we have? We can have dipole and induced dipole interaction. So this is the type of interaction that you'd have between a polar molecule and a nonpolar molecule. What happens is, if a polar molecule comes nearby, so if you have a polar molecule here, partial positive, partial negative, let's say you have a nonpolar molecule over here. What's going to happen? When the negative approaches, the negative end of a polar molecule approaches, what will it do to the electrons in here? It's going to push those electrons away, right? Electrons repel each other. So we have here, you would have an induced dipole. Okay, so a polar molecule, when it comes near a nonpolar molecule, it could cause the nonpolar molecule to have an induced dipole. It could so it could cause polarization of the nearby nonpolar molecule. So that's another type of interaction that could lead, then you'd have attractions between the two. Okay, so for which of these pairs would you expect dipole-induced dipole interaction? Between a pair of water molecules, between a pair of CO2 molecules, or between water and a CO2 molecule? Very good. Water is polar, CO2 is nonpolar. See, water and CO2 are the most popular molecules you'll find on a test, so you should be good friends with it, huh? Water is polar, CO2 is nonpolar. All right, so let's talk about hydrogen bonding. I mentioned this earlier when we talked about H2O and H2S, and there was an anomaly in our predictions. And then that anomaly, okay, is due to what we call hydrogen bonding. Okay, this hydrogen bonding is an interaction that occurs between two molecules. One molecule has a hydrogen that's attached to one of the three most electronegative atoms. The three most electronegative atoms are fluorine, oxygen, and nitrogen. Okay, so these are the most electronegative atoms. So anytime you have a hydrogen, here's a hydrogen attached to an oxygen, this one right here is a very polar bond. So anytime hydrogen is attached to fluorine, oxygen, or nitrogen, the bond is very polar, so there's a very highly positive, partial positive charge on the hydrogen. So it's almost bare of electrons. The electrons are almost all the way to the other side, to the oxygen, the fluorine, and the nitrogen. So that makes it very attractive to a neighboring molecule that has a lone pair of electrons. So if you have another molecule nearby, and there's an oxygen, a nitrogen, or a fluorine, like a water molecule nearby, that water molecule nearby, the lone pair in that is going to be strongly attracted to that hydrogen. That interaction is called hydrogen bonding interaction. That's a little bit, that's significantly more significantly stronger than your London dispersion forces. So that explains the anomaly between H2O and H2S. You would have expected H2S to have stronger attractions based solely on the size of the molecule, London dispersion forces. But water molecules have these additional attractions for each other resulting from hydrogen bonding interaction. Okay? So that would be what hydrogen bonding interaction is. Okay? In fact, in the case of water, you have this extensive hydrogen bonding interaction. Let's look at this water molecule right here. Here's oxygen, there's hydrogen, and hydrogen. See, this hydrogen can interact with that oxygen. This oxygen can interact with that hydrogen and the neighboring water molecule. This oxygen and that hydrogen and the water molecule can interact. And this hydrogen can interact with the oxygen of a neighboring molecule. So you have a very extensive network of hydrogen bonding interactions within a sample of water. That's why water has an unusually high boiling point. If there wasn't any hydrogen bonding interactions among water molecules, H2O is smaller than O2. Okay, water would be a gas. We're not going to have any liquid water if it were not for hydrogen bonding interactions, at least under ordinary conditions. Okay, it will take a very, very low temperature to liquefy your water. So under ordinary conditions, you're not going to get any liquid water. So that explains why water has an anomalously high boiling point. Okay, so let's look at this question right here. How many atoms in the acetic acid molecules shown here are capable of hydrogen bonding interaction with water molecules? So if there was a water molecule nearby, okay, what type of atom is capable of hydrogen bonding interaction? A hydrogen that's attached to fluorine, oxygen, or nitrogen. Do you have any hydrogens here that's attached to fluorine, oxygen, or nitrogen? Which one? This one, right? This is oxygen. This is oxygen, that's hydrogen. That's carbon, oxygen, hydrogen, carbon, hydrogen, hydrogen. CH3COOH. So this hydrogen right here would be attracted to a water molecule nearby, and so it will form, so that interaction between that hydrogen and that acetic acid molecule with the lone pair on the oxygen of a neighboring water molecule is what you would call a hydrogen bonding interaction between these two molecules. Okay, so that's capable of hydrogen bonding interaction there. Is there any other atom here that's capable of hydrogen bonding interaction? I'll give you another one. Okay, remember your oxygen has two lone pairs, right? Well, what if there's a neighboring water molecule that has remember in a water molecule, your hydrogen is attached to an oxygen, right? So that can be a hydrogen bonding interaction right there. So, to answer this question, how many atoms in this molecule are capable of hydrogen bonding interaction with water molecules? Is it 1, 2, 3, or 4? I've shown you 2 already, so it's not 1. Is it 2, 3, or 4? Where's the other one? Here's another oxygen atom, so it's got 2 lone pairs, so that would be attracted to a water molecule by way of the water molecule's hydrogen. Anything else there that has a lone pair? That's it. CH3COOH is this structure right here. Okay, so this is capable of hydrogen bonding, this is capable of hydrogen bonding, this is capable of hydrogen bonding. 1, 2, 3. Which one? This one?
Yeah. Like the one on the top has.
Oh, I just drew it differently. Let me redraw it. The answer was 3, right? I just drew it. Okay, so the way this is shown right here, okay, that's C double bond O. I'm sorry, C O H, and that's the double bond O right there. See, that's a double bond right there. That's a single bond. Okay. The fact that this carbon has a steric number of 3, there's only 3 groups sticking out of it, tells you that one of these would have to be a double bond, and it's this one right here. Okay. So you have to review your molecular structure. Okay. What about these hydrogens right here? Why aren't they capable of hydrogen bonding? These are not capable of hydrogen bonding because the hydrogens are not attached to fluorine, oxygen, or nitrogen. They're attached to carbon. A carbon to hydrogen bond is a nonpolar bond, essentially nonpolar. Okay? So that hydrogen is not very attractive to an electron pair on a neighboring water molecule. So correct answer here is B. So how do you explain why O2 is a gas while water is a liquid at room temperature? What type of interactions do O2 molecules have for each other? Does it have dipole-dipole interaction? Let's compare a pair of oxygens versus a pair of water molecules. Dipole-dipole. Oxygen. It's nonpolar, right? Water molecules can have dipole-dipole. Hydrogen bonding. None. Water molecules can have hydrogen bonding interaction, right? What else? London dispersion forces. They both have London dispersion forces, but they're both small molecules. So the anomaly really here has to do with the hydrogen bonding. You would expect actually O2 is a little bit bigger than H2O. Okay. You would have expected stronger London dispersion forces, but water molecules have an unusually strong attractions for each other because of hydrogen bonding interaction. Okay, you can also use intermolecular forces to explain solubility. When two substances interact, the interaction depends on how well do they like to stay among their own kinds, attractions among like molecules, and how strongly they would like to mingle with the other types of molecules. So interactions between unlike molecules versus interactions between like molecules. So in terms of solubility, for you to be, if you want to explain why does something dissolve in water and why does something else not dissolve in water, that you can explain that using the rule of thumb that's known as like dissolves like. So if you have a molecule that's very similar to water, they can interact with water the way water would interact with other water molecules, you would expect it to be soluble in water. Okay? But if they're not able to interact strongly with water molecules, so the structure is very different, then more likely it's going to be insoluble in water. Okay? So since water molecules are polar, okay, substances that are made up of small polar molecules will tend to be soluble in water than they would be in a nonpolar solvent. Similarly, if you have nonpolar solvents, if you have polar solutes, your solute molecules will tend to stay amongst themselves rather than interact and mingle with those nonpolar molecules of the solvent. So like dissolves like. So how do you explain why ethyl alcohol is soluble in water but vegetable oil is not? Ethyl alcohol, this is the structure of ethyl alcohol. Can you see how that's very similar to water molecules? They're capable of hydrogen bonding interactions with water molecules. So they can blend in, you might say, among the water molecules. Okay? So they can mingle easily with water molecules. What about vegetable oil? Now, the structure must be very different. Vegetable oils are a very long chains of carbon and hydrogen atoms. Okay? Carbon atoms is a hydrocarbon with a COOH at the end. Okay? So this very long part of your molecule, so this will be an example of fatty acid. Okay, each corner here you have a carbon atom, and then you have hydrogen atoms attached to those carbon atoms. So this carbon has 2 hydrogens, this carbon has 3 hydrogens. So each one of these corners is a carbon atom with hydrogens attached to it. Okay, so this is a very long, you might call a hydrophobic part of the molecule. So you might call it a hydrophobic tail of the molecule, which will not interact well with water molecules because these are mostly nonpolar bonds, right? So that's the explanation why oil and water don't mix, because it has to do with the structure of the molecules. Okay, they're very dissimilar, very different. Now this part of your fatty acids can interact with water molecules. So in fact, what you can do, if you put those in water molecules, they tend to stick up at the surface of a water. If you have a small drop of oil, those water molecules would stick up, and these tails would be sticking up, and this, you call this head right here, this is what you would call the hydrophilic part of the molecule. Why is it hydrophilic? Phil means, okay, hydrophilic means water-loving, right? Like Philadelphia, city of brotherly love. Phil means love, okay? A bibliophile is someone who likes books. An audiophile, someone who likes music. Okay, so Phil means to love, right? Pedophile would be, wow. Okay. So, bad joke. So if you have this thing right here, so this part of your molecule would be attracted to water molecules. How? How will this part of the molecule be attracted to water molecules? You can have hydrogen bonding interaction, right? Okay. And phobia, water fearing, right? That part of the molecule will stay away from the water molecules. All right. So here's stearic acid. It's a fatty acid. Is this likely to be soluble or insoluble in water? You have a very huge hydrophobic part, a very huge nonpolar part, so you would expect this to be insoluble in water. Okay. Which of the following is least soluble in water? NH3, HF, or CH4? How would you determine this? NH3, and then HF, and you have CH4. All right. So which one is least soluble in water? Very good. Why? This is nonpolar, right? Not capable of hydrogen bonding interactions. Whereas this fluorine right here, that lone pair can be attracted to water molecules by hydrogen bonding, and that hydrogen can be attracted to a water molecule also by hydrogen bonding, right? Same thing with the NH3, and this is also polar, okay? NH3 is also polar, and it's capable of hydrogen bonding interaction with a water molecule. Okay, so I have a water molecule here that can interact with that hydrogen because this hydrogen is attached to a nitrogen. Anytime you have hydrogen attached to fluorine, oxygen, or nitrogen, it's easy to remember. Phone, okay? Fluorine, oxygen, or nitrogen, the three most electronegative atoms. Then that hydrogen is capable of hydrogen bonding interaction with a neighboring molecule that has oxygen, nitrogen, and fluorine with a lone pair. Okay, so water, for example. In which solvent is iodine more soluble, H2O or CCl4? What's iodine? nonpolar, okay, and water, you know water by now, and CCl4, in which solvent is iodine more soluble, H2O or CCl4, A or B? Remember the rule, like dissolves like. Correct answer is B. Somebody pick C. More soluble in CCl4. This is nonpolar. This is polar. And this is nonpolar. CCl4 is a tetrahedral structure. It has polar bonds, but the molecule as a whole is nonpolar. Okay? Now, when you have large molecules, okay, most of the large molecules you'll encounter would involve long chains of carbon atoms. So each of these corners right here is a carbon atom that has hydrogens attached to it. Okay, and you have oxygen and nitrogen. You've got lone pairs on these nitrogens and oxygen. You have 3 lone pairs on this oxygen. Okay. And so the parts of the molecule that have the oxygen and the nitrogen with the lone pairs are what you might call the hydrophilic parts of your molecule. Those are the parts of the molecule that are capable of hydrogen bonding interaction with water, right? So like if you have an oxygen with a lone pair, it will be attracted to a neighboring water molecule, the hydrogen of the neighboring water molecule. The rest of the molecule would be what you would call hydrophobic. Now, when you have these large molecules, the more hydrophilic parts it has, the more likely it's going to be soluble or miscible with water. Okay? If a molecule has no hydrophilic parts, you expect it to be insoluble in water. So this molecule that I've drawn here, okay, do you think this molecule would be soluble or insoluble in water? It would be, it's got a lot of hydrophilic parts, right? So you'd expect this to be soluble in water. And I think at some point in your life you've ingested a bunch of these, a lot of these already. This is FDNC red. Okay, red 40. They use this as a artificial coloring for it's a food dye. This is FDNC, means food, drug, and cosmetics. It's an approved dye, red 40, Kool-Aid, all those red-colored products that you've ingested. Chances are they have FDNC red 40. Okay. All right. How do you explain solubility of ionic compounds in water? Okay. When you put an ionic compound in water, okay, they would tend to dissolve, and the reason for the dissolution is that your ions can have strong attractions for water molecules. So if I have a positive ion, which part of the water molecules would be attracted to it? The oxygen end or the hydrogen end? The oxygen. So an oxygen here would be attracted to that, right? So that is what we would call an ion-dipole interaction. The ion is attracted to your water molecule, which is a dipole, polar molecule. Okay, so your positive ions would be surrounded with water molecules, with the oxygen end of your water molecules attracted towards the positive ion. What about your negative ion? Which end of your water molecules would be attracted to it? The hydrogen end of your water molecules would be attracted to it. So Those types of interactions are called ion-dipole interactions. However, you'll find, okay, in fact, you've learned about solubility rules for common ionic compounds. There are some ionic compounds, or a lot of ionic compounds, in fact, that are not soluble in water. Why is that? Well, the reason is, although the ions interact strongly with water molecules, they can mingle with the water molecules. In some cases, the positive and the negative ions, since they attract each other anyway, in some cases, the attractions among the positive and the negative ions are so strong that they'd rather be by themselves. Okay? So, remember, in an ionic compound, what do you have? You have positives and negatives right next to each other, right? There's very strong attractions holding those ions together in the solid. For them to actually spread out in the water and be surrounded by water molecules, the first thing you need to do is break those ionic bonds between them. So in some cases, those ions, the attractions among the ions themselves are so much stronger, they'd rather be by themselves than mingle with the water molecules. So you need energy to separate the ions in a solid. So the energy you need to separate these ions, okay, from the solid to the gas phase, that's known as the lattice energy. The lattice is the, when you look at this structure of a solid where you have plus minus arranged in a regular pattern, that pattern is called a lattice. Just like when you have a lattice pie, you have that structure shown, right? So if you have a regular arrangement of positives and negatives, positive, negative, you have what's called a crystal lattice. So you're looking at a competition then between ionic bonding in the lattice and ion-dipole interaction. So in some cases, the lattice energy is so strong, okay, that your ionic compound ends up being insoluble in water. Okay. So here's a couple of movies that you should talks about physical manifestations of molecular polarity. Let me see. That's the last one. So let's take a look at this movie. And so you can find that movie at archive.org, and then after we watch the movie, we're going to answer these questions, okay? So let me just pause this video so I don't have to repost a copy of that movie on YouTube. So I'm going to pause. So what were the 4 liquid streams that were tested with a charged rod? Water, acetone, carbon disulfide, and benzene, all right? So of the 4 liquids, which two liquids were attracted to the charged rod? Water and the acetone. Okay. The ones that were, why were these attracted to the charged rod? Because they're polar. Okay. And why did it not matter whether the rod was positive or negative? Because like if this was positive and that's negative and the rod here was positive, what happens? The negative would be attracted. But what if you have a negative rod? This thing will just turn around, right? This one will still be attracted to your rod. Okay? Which of the 2 substances, cis-dichloroethylene and trans-dichloroethylene, caused an increase in the charging time of your electrically charged plates? Which one affects the ability of your charged plates to store an extra electrons, extra charge? The cis, the polar molecule. Okay. So putting polar molecules between electrically charged plates affects what's called the capacitance, or the ability of your charged plates to store an electrical charge. Okay, so that's it. Okay, clarification regarding Linus Pauling's electronegativity scale. We said that he basically came up with a scale where he assigned a value of 4.0 to fluorine and 0.7 to francium, based on bond dissociation energies. Exactly what does bond dissociation energy have to do with electronegativity? Well, what Pauling found was that if you had a reaction between H2 plus F2, that gives you 2HF. That reaction is exothermic. What that means is the energy needed to break the HH bond and the FF bond, okay? The average of the energy needed to break the H2 and the F2 bond, it turns out is less than the energy needed to break the 2HF bonds, okay? So the difference, he attributed that difference, okay, to what we would call the ionic character of the HF bond. And so that, in a way, gives you a way of quantifying the concept of electronegativity. He said that the reason the HF bonds are harder to break is because of the ionic character in the bond. Okay, so based on that, he defined the difference in the electronegativity of the hydrogen and the fluorine as the square root of, so this is square root of the bond dissociation energy of HF, difference between the bond dissociation energy of HF and the average of the bond dissociation energy of H2 and F2. Now, if you use this is the unitless quantity where the bond dissociation energies that you plug in are in electron volts. Okay, so the experimental values for the bond dissociation energy of HF, H2, and F2 are 6.397 electron volts, 4.484 electron volts for H2, and 2.75 electron volts for F2. Okay, so if you plug in these numbers into this expression, you'll find that if you were to set, the difference is going to be 1.7, okay, between hydrogen and fluorine. Now, if you were to set the electronegativity of fluorine to 4.0, and then 4.0 minus 1.7, that would give hydrogen an electronegativity on 2.3. Now, based on various data, so he did not just rely on H2 and F2, he settled on the best possible values, and based on his original, based on his original work, Pauling came up with a value of 2.1 for H if fluorine was given an electronegativity value of 4.0. Okay, this EV to the negative 1/2 here, electron volts to the negative 1/2. That's just something you put in there so that the whole thing here, this whole expression comes out unitless. So electronegativity is a unitless quantity. Now, Allred and Pauling revised the electronegativity value of H to 2.2 in 1961 based on additional data. Now, there have been other scales that have been used to come up with electronegativities for atoms. One was done by Mulliken, and that one is based on the average of the ionization energy and the electron affinity. Now, Mulliken's scale can be scaled to match Pauling's values.